Hello everyone, so here are your notes for 10.3 using chords. So let's go ahead and get started with the first theorem, which says congruent corresponding chords theorem. So the first thing that we need to know about this theorem is that we need to be either working inside one circle or we are working inside multiple congruent circles. But so long as we are in either of these situations, whether it is case 1, inside one circle, or case 2, congruent circles, we can go ahead and we can actually use this theorem. Now, what does the theorem actually say? It says that if you have congruent chords, so for example, in our picture, we have segment YZ, and let's say that segment YZ is congruent to segment BC. So these are our congruent chords. And I'm going to go ahead and, of course, mark them in the picture as well. YZ is congruent to BC. Now, if this is the case, then here's what we are allowed to conclude. We are allowed to say that kind of like their corresponding arcs, or their related arcs, so arc YZ is going to be congruent to arc BC. And of course, I'm going to go ahead and mark those in the picture as well. Here is arc YZ, and here is arc BC. So basically, within one circle, which is what we have here, if you have congruent if you have congruent chords, then you can conclude that you have congruent arcs as well. Now, this theorem actually does go both ways. So instead of starting with congruent chords, we can actually start with congruent arcs. So in this very same circle, if we knew that arc YZ is congruent to arc BC, then we are allowed to conclude that the chords BC and YZ should also be congruent. Now let's go ahead and see how this is used in an example. Okay, so in example 1, it says in the picture below, circle P is congruent to circle Q. Segment FG is congruent to segment JK, and measure of arc JK is 80 degrees, and what they want us to find is the measure of arc FG. Now, before we get started, the first thing we need to note is the fact that they tell us that we have two congruent circles. The reason why this is important is because if this was not true, we could not use the corresponding congruent chords theorem. But because we are working with congruent circles, we can go ahead and use that theorem. Now, what did that theorem say? Well, if you have congruent chords, and in these two circles, I have a chord, FG, and they also tell us that this chord is congruent to chord JK. So because these two chords are congruent, we are now allowed to conclude that their related arcs are congruent. In other words, arc FG will be congruent to arc JK. All right. Now, another piece of information they gave us in the problem was that the measure of arc JK is equal to 80 degrees. But from the theorem, we were able to conclude that the two arcs, arc FG and arc JK, are congruent, which means that if we know the measure of arc JK, then we also know the measure of arc FG, which is also going to, of course, be 80 degrees. So that right there is our final answer for this particular problem. measure of arc FG is 80 degrees. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, so go ahead and double check over your answers. Now, this particular problem was a little bit different because it wasn't as simple as just setting the arcs equal to each other. Here's what we were given. We were given that the measure of arc AC is 150 degrees. So I went ahead and labeled that on the circle. Now, in the picture itself, we notice that there are two chords that are both 9 units long. This tells me then that both of these chords are congruent, and so I can make this conclusion and say that, oh, then that means that their arcs, arc AB and arc BC, must also be congruent. Now, if we went ahead and we actually added all 3 of these arcs together, which is what you see in this equation here, they should be equal to 360 degrees. Now, from this first equation to the second equation, though, you'll notice that I substituted the measure of arc BC with the measure of arc AB. The reason why we are allowed to do this is because, again, these two arcs are congruent based on the theorem from earlier. So I treat these just like variables, right? Just like x. So because I have 2 of them, I'm going to have 2 times the measure of arc AB. Continue solving, and we get that our final answer is 105 degrees for the measure of arc AB. All right, so let's move on to another theorem dealing with chords. Now, here's what this perpendicular chord bisector theorem says. If a diameter is perpendicular to a chord, then here's what it does. Then the diameter bisects the chord and its arc. Now, 2 very important vocabulary words you have to remember. Perpendicular means that we have 2 lines, line segments, rays, any of those, 2 of those, and they make right angles, okay? And then we also have this word bisects, which means to cut into 2 congruent parts. Okay, so let's kind of put this all together. It says that the diameter is perpendicular to a chord. So if we take a look at our picture here, we have the diameter, EG, and that diameter is perpendicular to the chord FD. This little symbol right here, keep in mind that the symbol stands for perpendicular. So this says diameter EG is perpendicular to chord FD. Okay, so because we have this, based on the theorem, here is what we are allowed to conclude. It says that the diameter bisects the chord. So what that means is it literally, EG will literally cut FD into 2 equal or 2 congruent parts. So what are those parts? That is segment FH and segment HD. And both of these are, of course, congruent to each other. Now, it's not just the chord that gets bisected, though. It's also the arc. So arc FGD, this arc here, also gets bisected, which means we should also have 2 congruent parts there as well. Those 2 congruent parts are going to be arc FG and arc GD. So that's what we're allowed to conclude from this theorem. If we see in the picture that we have a diameter and it makes a right angle or is perpendicular to a chord, then it bisects both this chord into 2 congruent parts, and it also bisects the arc into 2 congruent parts as well. All right, so let's go ahead and use this in example 2. Example 2 says, if segment JL is a diameter find the measure of arc HK. Great, so we know that JL here is a diameter. And while we're looking at this picture, we should note the fact that we have a right angle here, which means that the diameter, JL, is perpendicular with the chord HK. From the theorem earlier, we know that if this is true, if a diameter is perpendicular to a chord, this means that the arc and the chord have been bisected. Now, we're not going to worry about the chord because we are working with the arcs here. So I'm going to pay specific attention to the arc that is bisected. And the arc that got bisected is actually the arc that we're trying to find the measure of. And that's arc HK. Now, what are the two parts that are congruent? Those two parts are going to be HJ, arc HJ, and arc HJ will be congruent to arc JK. Because again, from that theorem, it says that if the diameter is perpendicular to the chord, the arc gets bisected. So, now that I know these two are congruent, these two arcs are congruent, I can write an equation based off of that. HJ, which is 11x, right? Here is HJ, it is 11x. This is going to be equal to JK, which is 70 plus x. And now what I'm going to do is I'm going to solve for x, just with some regular algebra. Let's go ahead and let's collect all of our like terms on one side of the equation. So I'm going to subtract x on both sides. 11x minus 1x is 10x's. This is equal to just a 70. Last but not least, we're going to go ahead and divide by 10 on both sides, and we get that x is equal to 7. Now, keep in mind that because we finished solving for x does not necessarily mean that we are done with the problem. The problem is asking us to find the measure of arc HK. And what we can see here is that the measure of arc HK is made up of two other arcs. So I can write an equation using the arc addition postulate, which says that the measure of arc HK is going to be equal to the measure of arc HJ plus the measure of arc JK. And then from here, we're going to do the same thing and substitute once more. So the measure of arc HK is going to be equal to HJ, again, that was 11x, and the measure of arc JK was 70 plus x. Now, I already know what x is, so what I'm going to do is I'm going to substitute x, or substitute rather 7, wherever I see an x. So we get that the measure of arc HK is going to be equal to 11 times 7 plus 70 plus another 7. And then we can go ahead and we can finish calculating this. We get that the measure of arc HK is equal to 77 plus 77, which is just 154 degrees. All right, two things to note. First, we have two of the same numbers down here, 77 and 77. This should be accurate because we know that the two arcs are congruent. So if one is 77, the other should also be 77 as well. Now, of course, you do not have to solve it this way at all. If you wanted to, you could have just substituted x into one of these expressions and then just made sure that you doubled the measure to find the entire arc. All right, so go ahead and pause this video here and see if you can give this one a try on your own. All right, so go ahead and double check over your answers. Again, from the theorem, we know that because the diameter is perpendicular to the chord has been bisected, which means that we have two congruent parts. Those congruent parts are HN and NK. Now, in the picture, they tell us that NK is 7, which tells me that HN should also be 7 since they are congruent. So in order to find the entire length of HK, all I need to do is add HN and NK together, which is just 7 plus 7. And so we find that HK is 14 units long. All right, now there is a converse or kind of like a flipped version of the perpendicular chord bisector theorem. Here's what it says. It says that if a chord is a perpendicular bisector to another chord, then the first chord, the one that was perpendicular and was doing the bisecting, is a diameter. Okay, so let me quickly go ahead and actually erase our center for a moment here. I don't want to deal with this just yet. Now, what I'm basically doing is getting rid of that center, because here's what we have according to this theorem. We have two chords. So because I got rid of the center, we don't necessarily know if segment RS actually passes through the center. At this point, it's just a chord. But if segment RS, or if chord RS, bisects chord ED, and not just that, if it bisects it, but it is also perpendicular to it, in other words, it makes a right angle with it, then we are allowed to assume that chord RS is actually a diameter. So, two things need to happen. Chord RS must bisect chord ED. So that's condition number one. And then the other condition that needs to be satisfied is that it also needs to be perpendicular. To the same chord it's bisecting. And if this is true, if a chord bisects another and it is also perpendicular to the same one, then the original chord that was doing the bisecting and is actually a diameter. So we're not going to see any examples for this particular theorem, but I thought it was pretty important that we knew that we could also use this to prove if a chord was a diameter, if we weren't sure just yet. Okay, moving into our very last theorem. And this theorem says that it's called the equidistant chords theorem. Now, this word equidistant, we've seen it once before, but let us review and recall what the definition is. Equidistant means equal distance. In other words, you have two objects that are the same distance apart from, say, a third object. So, very quickly, here's how we typically measure distance. If we have a line and there's a point not on that line, if I wanted to try and figure out how far away is this line, how far away is the point from the line, there's multiple ways to measure. I could measure the point to this part of the line. I could measure the point to this part of the line, or I can measure the point to this part of the line. The question is, which one of those is the correct distance? The way we would define distance is that it is the shortest pathway to another point. And so the shortest pathway here just so happens to be a perpendicular line segment that connects the line to the point. So this little segment right here represents the distance from the point to the line. And so this is what we will see when we work with this equidistant chords theorem. So let's go ahead and write down what the theorem actually says. So if we have two chords that are equidistant from the center, in other words, equal distance, then the conclusion we are allowed to make is that these two chords are congruent. Okay, so let's go ahead and let's actually relate this to the picture. So in this picture here, we have two chords, chord AB and chord CD, and their distances are marked here with segment FE and segment GE. How do we know this represents the distance? Again, it's because these two segments are perpendicular to the chords themselves. So if these two segments, GE and FE, which again, these represent distance of the chords from the center. If GE is congruent to FE, then the conclusion we can make is that our two chords, AB, is congruent to CD. Okay. So, again, if the distance from the center, which is represented by these two line segments here, are equal or are congruent, then the chords themselves are going to be congruent as well. Now, this is one of those theorems that actually does work, again, in both directions. So instead of knowing that the chords are equidistant, if you knew that the chords were congruent, then they are equidistant from the center. So if we start with the fact that the chords are congruent, then we can conclude that the two chords are equidistant from the center. So if my two chords, AB and CD, are congruent, then their distances, segment GE and segment FE, must also be congruent. Now, one thing that I want to mention as well, just a little side note, is that these distant segments, so GE and FE, they actually do bisect our chord as well. So I'm going to go ahead and note this down. Segment GE bisects its chord CD, and segment FE bisects its chord, which is chord AB. Okay, so just keep this in mind because we will need that very fact to do a little bit of calculations and solving in the next example. Okay, so in example 3, we're going to go ahead and we are going to use the provided information below to find the length of the radius of circle C. Okay, so there's kind of a lot, so we probably should mark this down in our circle and do some labeling. First off, they tell us that YZ is equal to BC is equal to 16. So that tells me that YZ, which is a chord, and BC, which is also a chord, these two chords are congruent and they both measure 16. Okay, and I'll go ahead and mark this up here just as a reminder. These are congruent chords. Okay, so what they also tell us is that AP is 2x and AM is 5x minus 9. So let's go ahead and mark those down in the picture as well. AP is 2x and AM is 5x minus 9. Now, from the previous theorem, we have congruent chords and we have two segments, AP and AM, which are perpendicular to these chords. And because they intersect with the center, these segments represent the distance. And because the chords are congruent, this tells me that my two distances must also be congruent. Okay, so let's go ahead and actually write a statement that says exactly that. Segment AM, which represents the distance from chord BC to the center, is congruent to segment AP. And these are, again, distance from the center. Okay. All right. Because of this, we can now do some substitution into an equation. So AM, which is 5x minus 9, is going to be equal to AP, which is 2x. Again, collecting all of our like terms onto one side of the equation, I'm going to go ahead and subtract 2x on both sides. 5x minus 2x, that gives me 3x. Minus 9 is equal to, keep in mind that when these cancel, they don't actually disappear, they just become 0. 2x minus 2x is 0. Let's go ahead and add 9 to both sides of the equation. We get 3x is equal to 9. And then last but not least, we're going to go ahead and divide by 3 on both sides, and we get that x is equal to 3. But let's double check to see if we had finished the problem. Oh, and it looks like we didn't, because they wanted us to find the length of the radius. Here, if we're taking a look at this picture, we can notice that none of these line segments are actually a radius, because none of them go from the center to a point on the circle. But just because it doesn't exist doesn't mean that I can't add it to the picture. So here's what I'm going to do. Y is a point on the circle, and I'm going to connect it to the center. I've basically created a radius. And what happened when I connected and made this radius is that I now have a right triangle with 3 side lengths. So what I'm going to use to solve for the radius is the Pythagorean theorem. Because I have AP, it's 2x, but I also know what x is, so not worried about that there. And here's what I was mentioning earlier. This chord, YZ, gets bisected at point P. So YP, which is just half of the entire chord, is going to be 8 units long. And then, of course, like I said, let me substitute quickly to find AP. I'm going to say 2 times 3, because that's what x is, and this gives me 6. All right, so let me go ahead and I'm going to kind of redraw that triangle that we're working with off to the side to kind of make it a little bit more clear. So here's that right triangle. There's Y, this is P, and this is A. AP is 6, YP is 8, and what I'm looking for is the the radius, which is technically also the hypotenuse of this right triangle. So, like what I was saying before, because we're solving for a side on this right triangle, we're going to go ahead and we are going to use the Pythagorean theorem. So, a squared plus b squared is equal to c squared. Now, again, the side that we're missing is the radius, but it is also technically the hypotenuse. So I'm going to go ahead and substitute in 6 for a, so we get 6 squared, plus substitute in 8 for b, which gives me 8 squared is equal to c squared. You can go ahead and use a calculator to finish up the rest of this problem, but I'm going to go and finish it on screen. We get 36 plus 64 is equal to c squared. 36 plus 64 gives me 100 is equal to c squared. And last but not least, to get rid of that square right there, we're going to go ahead and square root both sides because that's the opposite operation of squaring. And what I get is that c is equal to 10. But in order to make it extremely clear, I can say that the length of the radius is 10 units. All right, and that is example 3 all worked out in its entirety. Again, the key here is kind of to draw in your own radius, and then we had to work with Pythagorean theorem, but we had to also make sure that we knew 2 out of the 3 sides, and that involved solving for x. So that's why we went ahead and solved for x first, so that we can get the second side, the measure of the second side, and then figure out the radius from there. All right, so go ahead and pause the video one last time and see if you can give this one a try on your own. All right, so go ahead and double check over your answers. I tried to make sure that everything fit on screen. Again, there's a lot of stuff going on here, but both of these chords are congruent and they're both 24. And because they are congruent, then that meant that I knew that my distance from the center was equal, or rather they are equidistant, which told me that NT is congruent to NP. So when I went ahead and set 3x equal to 7x minus 12, I went ahead and finished solving for x. And this gave me the segment NP when I substituted in. So that was 9. KP, which again is half of the entire segment, is 12. And then I went ahead and redrew that triangle with the radius so that it was easier to see which triangle we were working with. So substituting into the Pythagorean theorem, we got that c at the end of the day was equal to 15. But again, just to make sure that we are very clear with what we were solving for, I went ahead and wrote a sentence that says that the length of the radius is 15 units. All right, so that is it for your notes for 10.3 using chords. Thank you very much for watching.